Hi guys, I'm Brad Jackson, and this is Blue, and you're watching the Jacksunday Show. My name is Brad Jackson, and whether I'm flying airplanes or building pedals, I'm always learning. Join me, and together we'll expand our horizons. This is Jackson Audio. Alright, let me put this back real quick. Just don't pee, okay? Be cool. Okay, so last week we were at Sweetwater with Juan, Josh, and our very special guest Mateus. It was an awesome week at Sweetwater. We gave presentations for about 2 days, talked to a lot of the sales engineers, had meet and greets, just had a wonderful time. Got to do some videos with Mateus and eat a lot of really good food with some very dear friends. So last week was very cram-packed, full of activity, but very good activity and very fun. So that's what's been going on last week. You okay, Blue? Okay. He's good. All right, this week is our very first installment of Talk Nerdy to Me.
This is a whole new level of nerd.
Safety glasses on.
My calculations are correct.
21 gigawatts!
You're gonna see some serious
Today we're going to go through pedals that are described as digital control of analog pedals. What does that mean? How is it done? We're going to go through all that today. Show ways that work very well, show ways that don't work so well, and really dive deep into a fascinating little device called a light-dependent resistor and how it allows a microprocessor to control an analog signal. Very fascinating stuff. Stay tuned. All right, guys, in the intro I talked about how people do the whole digital control of analog pedals. Some of the new products we're working on have a lot of that in it, and some of the products I've been working on since 2017, like even the high rise we talked about, that's full of this kind of stuff. So, okay, digital control of analog devices. Well, let's take this pedal for one. This is something I'm working on, and there's two halves. This is the analog half. This is the digital half. All the digital half is a bunch of pots, talks to a big microcontroller. The microcontroller reads all the values, the analog values off these pots, and it does something with that information. That information can change depending on what I want to do at any given moment. So there's the digital side, this is the brain side, this is the analog side, this is what you actually hear. So we were at NAMM last week and people were talking about the Asabi and said, okay, how much of it is digital? Well, it's an analog pedal, but I control it digitally. So there's no digital signal processing at all. It's all analog. The audio portion of the pedal is 100% analog, but I control certain things via digital. So let me explain. Again, the microprocessor is the brain. You put code on this thing, and it executes commands, turns relays off and on, switches, analog switches to change different clipping modes, that kind of stuff. That's part of what you can do with digital control of an analog device. Now, the really big thing, the hard thing to do, is to integrate that digital control where you're actually grabbing values. Like, say, well, let's use the fuzz. Say you want to adjust your EQ to be 12 o'clock. Well, it'd be nice to be able to say that as a preset, and the microprocessor recall those exact settings. Well, you change this and this and this, and that would be nice to have that as a completely different preset. Well, that's not really doable with this because it's a 100% analog product. There's no brain inside this thing. It's just pots, and pots are just variable resistors that look an awful lot like that. I can probably show you better here on this one, but it's just a movable arm that you twist with 3 legs coming out of it, and as you change it, it changes the resistance. And it changes something in the analog circuitry, whether it's volume, gain, or tone, or whatever, any number of things. So years ago, back in 2017, when I started working on this kind of stuff, I was trying to figure out how is this all being done, because, well, you learn just a little bit about electronics, and then you realize there's these things called digital potentiometers, which is exactly what this is, except that it's controlled digitally. So I thought, okay, great, that makes a lot of sense. I'll try that. And all the digital pot is, I don't have one here, but if I were to point it out to you, it would look an awful lot like this. Probably like a 16-leg little chip that the microprocessor talks to, and it has several pots integrated into that little package. So you have essentially a digitally controlled pot. Now I tried those, I built a lot of circuits with it. I built several versions of the high-rise using digital pots, and it worked. It was all fine and good, but the issues I ran into was when you would roll the gain or any control, it wouldn't be an exactly smooth transition. That's the hard part, is the transitions. It wouldn't be a smooth transition. Say just pick gain. Say we're modifying the gain of a pedal. The gain transition wouldn't be a smooth step. It'd be kind of choppy, like you're walking up a step on stairs, and you'd actually hear it. You hear that. Brrr, brrr. That stuff's awful, because if you're trying to do stuff where you're expressing stuff, or you're just recalling presets, you don't want to hear a bunch of digital noise as you change those presets. So for me, digital pots didn't work. I tried several different manufacturers, several different protocols, whether it's I2C or what was it, SPI, I think it was. Tried different protocols, and they all did the same thing. So if any of you guys know off the top of your head how to do that where it doesn't make the stepping noise and what people call zipper noise, let me know, because I'd be really curious to know, because that would solve a lot of problems really in a really convenient package. So the next thing to play with are what is called light-dependent resistors. And light-dependent resistors have been around forever. You see them a lot in the tremolo circuits for old Fender amps. They used a light-dependent resistor to modulate the tremolo up and down. Very cool thing. Let's talk about what it is right now. This is a light-dependent resistor. It is nothing more than a resistor that is controlled with light, hence light-dependent resistor. They're really cool. They do a lot of things. They have a really high, when there's no light on it, it can go to several mega ohms of resistance. When there's a lot of light on it, it can go down to hundreds of ohms. So you have a really good dynamic range of value change. The trick with light-dependent resistors is how to get that to be controllable, because it's pretty wild as it comes out. As it is now, it's pretty wild and uncontrollable. So I figured out how to control all that stuff and do a pretty good job of it. But let's talk about what it is in reality. So it's really simple. This is an LED. You put voltage into it, it makes light. You're probably really familiar with what LEDs are. Well, if you take these two together and you marry them together, you shine the light onto the LDR, and now you can change the resistance of the LDR based on how much light you shine at it. Pretty cool, right? Well, these things, like I said, they've been around for forever. Typically, they look like this. This is the LED side. This is the light-dependent resistor side. And if you notice, they've got this whole thing wrapped up in a black plastic enclosure so that no stray light gets to it. Only the light that you want to gets to it. Because if you just do this, any spare light in the room is going to make its way to the light-dependent resistor and completely screw up what you're trying to do. It's not going to have the right resistance value. Now, you'll see a lot of guys that will roll their own, so to speak. They'll have an LED attached to a light-dependent resistor, they'll glue it together, maybe hot glue or super glue, and they'll wrap this whole thing in heat shrink and then shrink it all together, and you've got a great little approximation of this. This is about $1 or $2 a piece. They're not cheap at all. This right here is probably this is maybe like 5 cents for this and about 5 cents for this. So for 10 cents, you can approximate yourself what this guy is for $1 or $2. So if you're in production, that makes a huge difference. So in our pedals, what I have figured out is, rolling your own is cool, but still it's very, very time consuming. So what I have figured out is a way to do it by way of having 2 separate circuit boards. So let me show you what I'm talking about. On this particular pedal, this is the analog board. It's got a bunch of light-dependent resistors in the back of it. These are all controlling different elements of the pedal. And I've got the digital board. Well, what I can do is when I put it together, these little headers all join together and make one big sandwich out of everything. So I surmise this. Instead of rolling your own, or certainly even buying your own, I figured out a way to make this kind of a proprietary solution. It's kind of cool. So what I did was I went to China and specially ordered these little black plastic sleeves. They're just 5mm sleeves. And if you think about it, this is about 5mm. You pop that down in here, pop the LED in here. Hey, look, you just made a Vactrol, and you probably spent 15 cents on all of it. That works great, but you still got to have some way of controlling the light coming in this side, because you'd be surprised. You wouldn't think Stray light would actually make its way in here, but it absolutely will. And you got to be able to shield this side as well, or you're not going to get the resistance response that you do want. So check this out. This is what we did. If I have my LDR, and this is still a prototype, we're still working with a bunch of stuff, but it's good information. You take the LDR, it's right here on the board, drop the plastic sleeve on top of it, and then you put the little digital board on top of it. And what you have, you just made yourself a light dependent resistor with that little black tube right there. So no light can get in or out because the circuit board is sized perfectly between these two circuit boards. Super economical, saves a lot of money, works perfectly. But I took it one step further. If you look on the underside of the digital board, these little tiny squares, those are actually LEDs. Those are RGB LEDs that I can control. So, which is really neat because I have RGB, I can make any color from off to pure white based on the values I send to the RGB LEDs. So now, when I put the little shield in place and I put the digital board back down on it, I've created a Vactrol that I can vary my colors on. And that's really, being able to change the color is how you get a lot of control out of your LDRs. Whether if you just shone a red light on it, you would get one resistance curve, and you can get pretty close to ideal. But by being able to change the color of the LED from red to blue to green to whatever, I can actually map out a really accurate and a very linear line of resistance. Let me try to explain what that means. Okay, so I've got an analog ohm meter here. An ohm meter, all it does is it measures resistance. So what I have here is some leads. I'll grab some leads over here. And what we're going to do is we're going to give you a pretty practical example of what an LDR does. I'm just going to attach these alligator clips to the ohm meter so that I can attach the other ends to this LDR. And watch the scale of the meter. So look at that. So that's like a mega ohm of resistance. If I take my hand off it, it goes to like 200K. So just by moving your hand nearby, not even changing the light source, you're massively changing the resistance. So that is a really kind of a quick and dirty version of what an LDR does. At that point, it's completely impractical. You can't do anything with it because depending on the color of the light, the intensity of light, the proximity of the light to the LDR, and even the model of LDR itself, you're going to get massive resistance changes. So it's really hard to make it a practical circuit. So the trick really is this, trying to get it to be a linear response. And by linear, I'll explain. Hold on. Okay, so let's imagine, if you will, that we are trying to make a 100K variable resistor. This would be something like you'd see in maybe a tone stack, or really practically, let's talk about an op amp or something like that. Just say you had a 100K resistor here, and you want to put a 100K resistor here. That's an op amp. So what that is, it lets you go from almost no output to unity output. So think of it like a volume control. Now what I can do, I can put an LDR across it. That's a really terribly drawn symbol for LDR. Alright, so check this out. I've actually got something kind of modeled up for you. This is really tacky and very crude, but it works to prove the point. Because the resistance of an LDR is typically measured in mega ohms, or a million ohms of resistance, we wanted to have a final or highest value of 100K. So what you can do is just strap a 100K resistor across the light dependent resistor. That means the most resistance it will ever have is 100K. Let's prove it, because if you can't prove it, it's not real. Hey, look at that. Exactly 100K of resistance. I got my finger over it, over the barrel, so it's perfectly dark. I take my finger off, it went to, what is that, 30K of resistance, but I'm modulating it now based on how much light I'm allowing to get to the LDR. So we're proving that it works. The trick is, we want this thing to be linear. So if I want to go from an ideal value of 0 ohms to 100K, well, we know we got 100K, but I need to get down to 0. You're not going to get down to 0. It's not really possible unless you do some really serious monkey business on an LDR circuit, but this is just a really good approximation just to teach you the core concepts of what we're doing right now. So put a 100K resistor across this. That sets the maximum resistance. Now we're limited to 100K. But what I want to get is a linear response. Linear meaning this, exactly. So if I want to modify, if I want to say spin a knob on my pedal and have this light dependent resistor go from 0 ohms resistance to 100K, this is where this all comes together. We want to get to linear. At my percent of rotation, which is say 0 rotation, 100% rotation, I want that ideally to correlate to percentage of resistance. So 0 rotation should ultimately, ideally, be 0 resistance, and 100% rotation should be 100% resistance, basic linear stuff. Right now what's going to happen is you're going to have a line that's like this. It's going to be super exponential. It's not going to be linear at all. So what you have to do is you have to start modifying stuff in the microprocessor by using lookup tables to say, okay, if I'm going to get X amount of resistance, I have to shoot this much light at it, this color, all that kind of stuff, have this much distance between it. That's where I'll leave it with you as far as the science of it, because that's, if you're interested in this kind of stuff, I really encourage you to jump in, get some of these cheap parts. They're everywhere. You go off Amazon, eBay, they're everywhere. Play with it, put them together yourself, mess with it, put 5 volts into it, see what it does at different voltages. Try using pulse width modulation, not just voltages. Pulse width modulation is this. It's signals that look just like this. They're digital. It's like 0 to 5 volt signals, but the duty cycle from off to on, how wide that duty cycle is, will determine how effective that LED is at driving the LDR. That's for you. If you have specific questions, please let me know. I'll be glad to help. But just so you guys don't completely gloss over and fall asleep, I'll just kind of keep it there. So anyway, that's what I've been working on since 2017. I've got a really good handle on it. And certainly all the projects we're working on now, definitely the chorus is going to have that kind of stuff on it. Some of the other projects that we're working on too are going to have it, because that's just super, super fun. Where you can take something like a really simple LED and control a light dependent resistor, use it to recall presets. It's a whole lot of fun. If I give away any more than that, I'm really starting to kind of like give away trade secrets, because it's been stuff I've been working on for many, many years to dial it in, and it's really dialed in now. It's really exciting, because now that the process is all figured out, we can really move ahead with taking that knowledge and making products with it. It makes it much more simple once we kind of climb this mountain of figuring out how do I quietly and accurately modify resistance changes to produce recallable presets. So anyway, you'll be seeing a lot of that from us in the future. Over the next year, you'll be seeing quite a few products like that use this kind of technology. If you have specific questions, please comment, let me know, because I love this kind of stuff. I can't talk to my wife about it because she just kind of glosses over, but if you have questions, if you enjoy talking about this kind of stuff, please talk nerdy to me. I love this kind of stuff. It's what I do all day and night here at my home office. So if I'm home, I'm working on this kind of stuff. I'm either working on hardware, doing a prototype of something, or I'm working on software for this kind of stuff exactly. So please hit me up with your comments. Thanks for watching. All right, that has been Talk Nerdy to Me. As always, I'm Brad Jackson with Jackson Audio. Thank you for watching. Stay tuned next week for the next episode of the Jacksunday Show. Talk to you soon. Bye-bye.